Alright, we're going to take a look at our example for our strong base and weak acid. And you could think of this as a strong acid, weak base, or we can flip these. So these can go in any order, but it's basically a strong with a weak. The molecular equation we're going to take a look at, our strong base is going to be lithium hydroxide. I'm going to go ahead and label each of our acid and base aqueous because we tend to have them come as aqueous solutions. And then our acid is going to be hydrofluoric acid aqueous. So when we look at these, we're going to be memorizing our strong acids and bases, like I've said, and our lithium hydroxide is one of our strong bases. And then hydrofluoric acid is not on this list, so it is weak. So I'm just going to write underneath this weak so I know which one it is. We can recognize our base as having this hydroxide on it and our acid as having that hydrogen out in the front. Sorry about that. Alright, and our acid has that hydrogen in front. So again, we're going to do our double replacement. Hydrogen and lithium, our positive ions, are going to switch places. So hydrogen and hydroxide are going to make that water molecule that's liquid. And then we have lithium and fluoride. Lithium, fluoride. Lithium is positive and fluorine is negative. So if we did our crisscross or looked at our charges, we just need one of each. Now, lithium fluoride, we would need to check its solubility on this to decide its state of matter. This is not on your solubility rules, but just so you know, our solubility of our alkali metals, the metals on the left side of our periodic table over here is the lithium, sodium, potassium, rubidium. Basically, their rule is that they're always soluble. There are very, very rare exceptions where they are not, but we're not going to really run into any of those, so don't worry about it. Assume that your alkali metals are going to be soluble. You've noticed probably in your exceptions on your solubility rules that the alkali metals are exceptions to everything. We have two of our alkali metals, sodium, potassium, as part of our solubility rules to memorize. They're always soluble. So that's those alkali metals. So we're going to go ahead and put aqueous for lithium fluoride. We take a look at it. It is balanced. We've got one kind of everything except for our hydrogens, but we have our two hydrogens here. So we are okay on the balancing. Now we're going to move into our ionic equation. So we want to break down things that are aqueous, or in the case of acids and bases, only the chemicals that are strong. So our base here is a strong base, so lithium is going to separate from its hydroxide ion. We're going to separate them. They both need their charges, and they both need their states of matter. Their coefficients are both 1 because there's one of each in this chemical. And then our acid in this case is weak. Our weak acid or our weak base is going to stay together as a compound. So we're going to go ahead and just copy HF down and its state of matter. Not do anything with it. Alright, on the right side, our water is a liquid. It's going to just come down and it's going to stay together. Nothing changes about that. And we decided that our lithium fluoride was soluble, so lithium separates with its charge and state of matter from fluoride with its charge and state of matter. So it's hard to all fit it in one shot, but we've got our complete reaction here with that aqueous fluoride at the end. Our next step is to create that net ionic equation. Our net ionic equation, we're going to leave out any spectator ions. In this case, our only spectator is lithium. Lithium is the same on both sides, both aqueous, both ions. We can take a look. Our hydroxide becomes part of our water. Our HF is together here, so it's not ions. We can't cross anything out, even though it's labeled aqueous. So very close thing to check here. We've got this fluoride, it's aqueous. We've got this fluoride, it's aqueous, but one of them is trapped in a compound and one of them is an ion. We can't cross that out. They both have to be exactly the same. So we're going to leave out lithium and bring down everything else. So our hydroxide ion with its state of matter, our hydrofluoric acid, method state of matter, our water, liquid, and our fluoride ion. That would be our net ionic equation for this strong base and weak acid. So when we had a strong acid and a strong base, we were able to cross out more spectators. When we have one of them weak, kind of eliminates one of our spectator ions, and we get less there to cross out. All right, we're going to do one more example. We are going to do an example where they're both weak, so weak acid, weak base, or weak base, weak acid. I'm going to choose phosphoric acid, one we might not have seen before. So our phosphate ion, PO4, has a 3- charge. So to make it an acid, we need three hydrogens to balance out its charge. We're going to go ahead and put aqueous. And let's use, I need a base. Let's use magnesium hydroxide. All right, magnesium hydroxide. Magnesium is a 2+ charge. Hydroxide is minus. So we would crisscross that charge to write this properly. Remember, we don't want to actually show those in our molecular equation. All right, aqueous. All right, products here. Acid and base, we're going to make water. We've got hydrogens and hydroxides. It's going to give us water molecules. And you can always see we already have extra hydrogens and extra hydroxide. We'll probably have to balance this equation and put some coefficients in front. Water is always a liquid for our acid-base reactions. And then our other product is magnesium and phosphate. Now again, your magnesium is a 2+ charge, so magnesium is 2+. Phosphate is 3-. So if we wrote this correctly, we have to crisscross those charges. We get Mg3, bring down the 3, PO4, because that's our phosphate, and we have 2 of them. So we write Mg3, PO4, 2. Oops. And we are going to take a look at our solubility for this. Phosphate is one of our solubility rules. We don't see it too much, but it's there. So phosphate is typically insoluble. It's going to create a solid. And magnesium is not an alkali metal. It's not ammonium. So this is going to be our solid in this case. All right. So I know I can't get this all in one shot, but that is our complete reaction. Now we do need to balance this reaction. Let me see if I can get this smooched up so you can see. All right, so we need to balance it. I'm going to start with my magnesiums because that seems like an easy place. So we got 3 magnesium over here, and we've got 1 on this side. So we're going to put a 3 out front. Balance those magnesiums. Coefficients. All right, so now we have 3 magnesiums. That changes our hydroxide here as well. We'll get to those. Let's do our phosphates as well. So we have 2 phosphate on this side. We need to have 2 on this side. So we need a coefficient 2 out in front. Now what this does is gives us 6 hydrogens, and we have 3 times 2 is 6 hydroxides. So for every 1 hydrogen and 1 hydroxide, we make 1 water molecule. So if we have 6 of each, we're going to make 6 water molecules. Makes it kind of easier to balance. All right, so we're going to break this down into its net ionic equation, or excuse me, its ionic equation. And we got lots of ions here, or we have lots of chemicals here. Now, our acid and our base are both weak, so that means that we cannot break down either of those chemicals. So we just copy it down. H3 PO4 aqueous. We have water here, and it's a liquid. We cannot break that down, so we copy it down. And then we have our magnesium phosphate here, and it's a solid, and we copy it down. So, guess what? Nothing changes. Well, It's not that nothing changes. We do have a reaction that occurs. We make water, we make magnesium phosphate. It's just that our products here, we got this magnesium phosphate and water. That's all we've created. And nothing broke down into ions, which means our ionic equation is exactly the same as our molecular equation in this particular case. And nothing cancels out. We have no ions. So our net ionic equation would also be the same. We've had some before where we ended up with everything aqueous and everything ends up ions, and we weren't able to cancel anything out, we canceled everything out basically as a spectator, and we'd write no reaction. Well, in this case, it's not that everything crosses out, it's that nothing crosses out. So it's still a reaction occurring, but it's that our reaction stays the same because we can't break anything down. So it's a little bit simpler. It's kind of nice. Whenever you have a weak acid and weak base, because these reactants are not going to ionize, we will not have spectator ions. So that kind of simplifies these a little bit. What can change is that we will still have this liquid water, but what can change is this final chemical. If it's aqueous, we would want to show it broken into its two ions at the end. If it's solid, then we just leave it together. So that's the main thing that will change, is that last chemical being either soluble or insoluble, and that will change whether it stays together or breaks down into ions. So that's our last example. Make sure you check out the other ones. Make sure you have all your notes. And I hate announcements. Okay. Then you're going to be doing the practice on this worksheet. So it's the chapter 4, aqueous reactions and solution. It's the acid-base equations. So if you don't have this, make sure you get it from class. So this is the same approach as we've done before. So solutions of hydrochloric acid and barium hydroxide. What you're going to want to do is write out your chemicals. Make sure you check their charges and make sure you've written them correctly. They'll both be aqueous because it says solutions. You want to make your products, and the biggest thing you want to do is, before you go from your molecular equation to your ionic equation, is check to see if these are strong or weak. For instance, hydrochloric acid is our first acid we're going to memorize. It's a strong acid, so I like to put strong acid right above this as a reminder. So I know that that will be broken down. It'll break apart, strong and independent. And barium hydroxide, so we look over here and we look for barium. Barium is Ba, so barium hydroxide is one of our strong bases. So it will follow the strong acid, strong base example. Both of those chemicals will break into their ions, will form that water and salt, like we've been doing, and be able to create our net ionic equation and everything. So the biggest thing you want to check is if they're strong or weak, and that'll tell you if they break down or not. If it's not on these rules, so if it's not listed strong acid or strong base,